don't have the access to Zoom in parts of India. So
oh, really?
they join.
I see. Okay. Oh, well, then it's good you do that. Yeah.
Okay, perhaps it's a good time to begin. So welcome everybody to this week's Majorana-Raychaudhuri's seminar series. Today's first speaker is Christian Byrnes, and from University of Sussex, UK, and he's going to talk about introducing primordial black holes. Maybe I'll send you a reminder when 5 minutes are left.
That's fine. Okay, well, thank you. Thanks for inviting me to give this talk. Right, I'm going to give a very broad general introduction, and so certainly not aiming at the experts, but rather at people who are quite new to the field of primordial black holes. This is just a picture of Brighton Beach and the pier. For those who don't know where the University of Sussex is, it's in the city of Brighton on the south coast of England. Okay. So primordial black holes, why am I interested in them? Well, because they probe the initial conditions and the contents of the universe. Black holes are cold and dark, so clearly they're, in a sense, a part of dark matter. But we know via CMB observations that dark matter needs to predate the formation of the CMB, while astrophysical black holes come after stars, right? Typically, they're dead stars. So an astrophysical black hole cannot make up a large fraction of dark matter, whilst a primordial black hole could be all of the dark matter. So what's a primordial black hole, or PBH for short? Well, it's a black hole which formed in the very early universe, typically before Big Bang nucleosynthesis, so less than a second after the Big Bang. And that gives some interesting potential properties. For example, the black hole radius scales like the mass. If you think of the famous formula for the Schwarzschild radius, 2gm, okay? So the density, taking the very simplistic idea of a uniform density, okay, is the mass divided by the volume, so it goes like 1 over the mass squared. Why is that important? Well, it means in astrophysics, there's a maximum possible density based on degeneracy pressures, for example, related to the Chandrasekhar mass, okay? So if you've got a maximum possible density, then there's a minimum possible mass that corresponds to, which is approximately the solar mass, and by coincidence, okay? Primordial black holes, on the other hand, they form in the very early universe when the density couldn't be arbitrarily large, so they're not bound to that limit at all. They also form typically out of radiation rather than standard model particles, or at least then sort of electrons and neutrons, etc., which are a small fraction of the background density at that time. So there's the potential for subsolar black hole mergers, which could be a smoking gun signature or evaporation of black holes. If they form really very light, they will, via Hawking evaporation, reach up to arbitrarily high energies. And I'll come to these topics. So this is a lot to cover in 35, 40 minutes, but I'll try to motivate that they could be all of the dark matter. Then the challenges of, in fact, doing that, of forming primordial black holes. And then I'll go from heaviest to lightest. So the ordering of supermassive black holes, then what LIGO, Virgo, Cagra could see, how that relates to the pulsar timing array observations and the asteroid mass window, evaporation, relics, and sort of multi-component dark matter. Needless to say, it's a huge topic, and I've worked on some aspects, but not on other aspects. So I'm going to focus on the things I know best and I enjoy the most. Apologies then for all the topics I neglect, references missed, etc. This is meant to be a personal review of the subject, not, comprehensive. There's a whole book, by the way, on primordial black holes if you want to learn a lot more. But first of all, so dark matter needn't be a new particle. There are constraints on primordial black holes being all of dark matter. So the vertical axis on this plot is FPBH, so it's a fraction of dark matter in primordial black holes. So 1 is all dark matter, 10 to the minus 2 means 1% of dark matter in primordial black holes. And as I said, if you have form with a relatively light mass, below about 10 to the 17 grams, then you would see the impact of Hawking evaporation. If you're about 5 orders of magnitude heavier or above, then you should see signs of microlensing, and I'll explain what that is in the next slide. And then when you get to much heavier masses around the solar mass, sorry, the bottom horizontal axis is in the mass and solar mass, the upper one is in grams. Cosmologists use both depending on the context. There are constraints from gravitational waves, from the impact of accretion onto black holes, which relates to the next talk in this series, or etc. But there is a window, which is not controversial, although people have wrongly claimed from time to time that it's closed, of roughly asteroid mass, where all of the dark matter can be in primordial black holes. And there's a nice review article, which I list here, where this plot comes from. So that's one of the headlines. When you talk to theoretical particle physicists, they typically say, you know, the standard model is broken. One of the reasons is that we need dark matter, and that must be a new particle. That may be true, but it doesn't have to be true. Now, that was assuming a monochromatic mass spectrum, so all primordial black holes have a single mass. When you go from monochromatic to, for example, quite a broad log normal mass function, one can redo the constraints, and more or less the constraints get smeared out. But the tightest constraints get a bit weaker. So like if you look at the tips of these points, they get a bit lower. But the asteroid mass window gets narrower because these constraints get broader, basically because it's saying, you know, if not all the black holes have a single mass, then if your peak was, say, here, with monochromatic mass spectrum, there'd be no constraint. But if you have a broad mass function, something like this, then you're not allowed to overlay with the microlensing constraints. Okay. The main result is really, even for more realistic broad mass functions, unless they're extremely broad, and there's no reason to expect they would be extremely broad, there's still a window. Okay, so what is this gravitational microlensing? Well, it's a lensing of the effect which is too small to be seen in terms of any distortion of the image. So this is not even weak lensing where you slightly distort the shape of the galaxy. It's certainly not strong lensing like this Einstein arc, but rather it's when you've got a relatively small mass object moving in between you and a background star. What happens is that although you can't see an Einstein ring in principle, in practice, the bending of light as the lens moves in front of the star will create a temporary brightening. And it's the fact that this effect is temporary and has a well-predicted light curve, which means that you can know if you've seen a microlensing event. You have to get lucky because this is a very small effect. So basically you need your lens, which may be a black hole, to move extremely close along the line of sight to really hitting, well, not hitting, but crossing the line of sight from you to the background star. Now, these asteroid mass black holes are tiny, they're atomic scale, and the Einstein ring is also very small. So you get just a little bit of brightening, and that's it. So it's a difficult observation. One important effect which had been neglected was that the background stars themselves have a finite size. And the calculation is normally done in what's called the point source approximation, so treating the background star as being a single point. But that's not always good enough, because when you're searching for extremely low mass microlenses, then you have to worry about whether it's a strong enough effect to in fact lens all of the background star or just some fraction of it. And when it becomes not all of the background star, then basically the temporary brightening goes to zero because you're only brightening some fraction of the surface of that star. And that's important because using this point source approximation, which is the most optimistic case, people had claimed more than once that the asteroid mass window was ruled out, excluded. And that's wrong. Okay. That's wrong exactly for that reason, that when you're getting to very light black holes, there, the Einstein radius, the effective size of the Einstein radius on the sky is smaller than the size of the background star, even when that background star is in, for example, the Magellanic Clouds or in Andromeda Galaxy. Yeah, this femto lensing, this is also not a correct constraint, so this should also be removed. But I'm just saying there is confusion in the literature. Also, sometimes people are not very clear about what's the forecast and what's an actual constraint. So on this plot, these are real constraints. There are no forecasts included here. Okay. So in that sense, you might be thinking now, well, a primordial black hole is very compelling in some sense. You don't need any new physics. So why doesn't the community embrace the idea that dark matter is primordial black holes? Of course, some people do, but many people don't. One issue, in fact, in my view, the biggest issue with primordial black holes is the challenge to form them. You need a very large density gradient to form a black hole. And we know on large scales, the early universe is extremely smooth. And it took of order 1 billion years for the first galaxies to form. But here we need these black holes to form in the first second, meaning that we need a very large primordial density fluctuation or some form of topological defect, such as domain walls or phase transition, to create these very large density gradients. And that's what's not generic. And assuming radiation in the early universe, which is the fiducial assumption, then you need an overdensity of order delta rho over rho of order 0.4, something like that, at horizon entry, to be compared with a few times 10 to the minus 5 on C and B scale. So we need the small scale fluctuations basically to be much more perturbed than the large scales. And that typically achieves some type of fine tuning, or at least something special in your initial conditions. What's nice though is if they do form, then there's a one-to-one relation, more or less, basically. At any time in cosmology, there's a horizon scale, there's a corresponding horizon mass, there's a corresponding temperature, there's a Fourier scale, K, etc. And there's a time, and the black hole which forms will be of order the cosmological horizon mass. Okay. So given a particular scale, if you say this is where my power spectrum had a large amplitude peak, much larger than the 2 times 10 to the minus 9, you can say, okay, well, on that scale, the horizon mass is such and such, so that will be the black hole mass. This is the time when they form, this is the corresponding temperature of the background universe, etc. So there's a lot you can learn. Maybe I can just highlight, I wrote some lecture notes together with Pippa Cole on introducing inflation and the link to primordial black holes. So if you want more details, you can look in here. And in fact, this is why I originally started working on primordial black holes. It wasn't to do with dark matter so much, but as a way to probe the initial conditions of the universe on scales which we can't observe via the cosmic microwave background, basically because of silk damping and resolution limits. You can probe of order 6 or 7 e-folds, meaning a range of scales of e to the power 6 or 7, approximately 3 orders of magnitude. Well, we expect roughly 10 times that number of scales on a logarithmic sense to have exited between the cosmological horizon today and the smallest horizon scale at the end of inflation. So we're really only seeing a very small fraction of the impact of inflation of scales leaving the horizon. So what can we do? Well, basically because of the large radiation pressures and densities, small-scale perturbations tend to be washed out, and there's nothing we can observe today unless we have a relic, which could be gravitational waves. You can ask Ganesh about that. He's much more an expert than me on that topic, or primordial black holes, which is what I've spent a lot of the last decade working on. Okay. So here we go again. Here's the cosmic microwave background on very large scales. Here we have a detection. Is there a question?
No.
Yeah. Okay. Okay, so we've got the cosmic microwave background, then we've got constraints from cosmic mu distortion. So basically, the Kobe-Firis instrument showed that the CMB is a black body to very high accuracy. And that's important because if we had very large amplitude fluctuations on the relevant set of scales, they would basically, in the baryon photon plasma, you would have damping of these large amplitude fluctuations. The damping would break thermal equilibrium, and that would break the black body distribution. Again, for some range of scales where you wouldn't be able to reach a new thermal equilibrium. So there are mu distortion constraints, which are very tight. I'll come to the pulsar timing array in a couple of slides. And then to form primordial black holes, given that you need the density contrast to be of order 0.4, you can calculate that you need the power spectrum amplitude or the variance to be of order 10 to the minus 2. The exact numbers depends on the shape of the peak, depends on your various other points about the formalism you use, but roughly speaking, 10 to the minus 2. So you need a growth of the primordial power spectrum by something like 6 or 7 orders of magnitude. Again, this is what some people find unattractive about the model, which is fair enough. Yeah. But as I say, just briefly, if you have an inflationary model, single fields, where you have some inflection point in the potential, then that leads to exponential instability. So as long as that instability is hidden, shielded from CMB scales, you could have a large growth on some smaller scale, and then you can form primordial black holes. However, it can't be too large, or you will overproduce them, or potentially even get stuck in eternal inflation, which of course would destroy the success of the inflationary model. Okay, so now I'm going to go relatively quickly from heaviest mass to lowest mass primordial black holes and tell you just a few things which in my view are interesting about them. So starting with the heaviest supermassive black holes, they're certainly observed. They're seen in the center of many galaxies. There's going to be a talk right straight after me, which I apologize I won't be able to stay for because I'm marking a huge number of projects. But they're seen in the center of many galaxies, even at high redshift. And so JWST, then, well, not so new telescope anymore, has seen this. It's disputed, but certainly beyond redshift 7, potentially up to redshift 10 or so. Meaning that somehow million to billion solar mass black holes are forming in less than 1 billion years. And in the standard model of cosmology, with standard initial conditions, with a 2 times 10 to the minus 9 primordial power spectrum on all scales, this is a difficult thing to explain. I don't want to say it's impossible, I'm not the expert. But to quote genuine experts on this field in a review, low mass seeds of black holes are common, astrophysical black holes, but high mass seeds, enough to explain the supermassive black holes, are rare and depend on processes which we have not yet observed. So we have this mystery. How do you get these very massive black holes very quickly? And of course, the temptation is to say, well, they're primordial. Problem solved. I wish it was that simple, but it really isn't. Why not? Well, remember the spectral distortions which I mentioned. The fact that you will destroy the nearly perfect black body spectrum. And we know since Kobe, so since over 30 years, that the CMB temperature mimics a black body to better than 1 part in 10 to the 5. It's really one of the most precise measurements in cosmology. Yeah, the fact that the cosmic mu distortion and cosmic Y distortion are both extremely small, that's really very precisely known. Meaning that we had a very, very good thermal equilibrium. Okay. So if you want to form these supermassive black holes, well, then the scales are really getting rather large. We're getting towards scales of, say, 1 million kilometers. And when you convert that into what scale would that correspond to, which redshift would this correspond to in terms of the formation, you see there the constraint on the primordial power spectrum, or the variance of the primordial fluctuations from the mu distortion being less than about 10 to the minus 5, whether for Gaussian perturbations shown in the solid red line or for highly non-Gaussian perturbations shown in the dashed red line, the constraint's about the same. It's very tight. It's better than 10 to the minus 5. You can then ask, well, which amplitude of fluctuations did I need to form even just, say, 1 part in 10 to the minus in 10 to the 10 of the dark matter to be supermassive black holes? And the answer is, you need a much larger amplitude again because this delta critical is of order 0.4. So you need something like 0.1, 0.01. If you go to non-Gaussian fluctuations, then you can suppress the amplitude, the primordial power spectrum amplitude, because you're boosting the tail of the perturbations. And it's the tail of the PDA, which forms the rare peaks, which collapse into primordial black holes. But even for something really extremely contrived, pure Gaussian cube fluctuations, which is not what you get in any model of inflation I've ever heard of, including not from standard stochastic sort of inflation models, it's just not enough. You still need your power spectrum to be larger than 10 to the minus 5. So unfortunately, forming black holes on scales, primordial black holes on scales larger than about 10 to the 4 inverse megaparsec are not, by the way, so K is 1 over length. So small K corresponds to large physical scales. We need to be on scales physically smaller, so large K, than where these lines intersect, where the mu distortion line becomes weaker than the primordial black hole line. So for Gaussian, we're somewhere like here, 10 to the 5, which corresponds to the mass, again, remembering that there's a one-to-one relation between scale and mass, of something like 10 to the 4 solar mass black holes. So my conclusion is forming primordial black holes with a mass more than about 10 to the 4 solar mass is extremely high. And for the standard formation mechanism really is ruled out, even for strongly non-Gaussian fluctuations. There are, of course, maybe ways around this, but they're very, in my view, let's say, very specific and perhaps contrived. Now, it may still be helpful to have seeds of 10 to the 4 solar mass, but one somehow needs to grow that seed, either by a huge number of mergers or by a huge amount of accretion to be at least 10 to the 6 solar mass. And some supermassive black holes, even at high redshift, are seen up to 10 to the 8 or 10 to the 9, perhaps even 10 to the 10 solar mass. So that's a huge growth. So it's not very clear how helpful it is to form these supermassive black hole seeds. Yeah, I'm trying to be honest here about, what are the goods and the bads of primordial black holes, rather than trying to sort of convert you all to work in this field. It's interesting, but there are lots of interesting, of course, topics in physics. Now let me move down in mass to around the solar, to 100 solar mass, and slightly subsolar mass. Okay, so LIGO, Virgo, and Cagra, they've seen many hundreds now of events of gravitational waves formed from very short time scales, typically a few seconds, when two compact objects come together and merge. We just see the gravitational wave signature in the last few inspirals, which is when the amplitude of the gravitational waves grows to the largest. So back in 2020, when there were just of order 10 events, Alex Hall led this analysis of doing a Bayesian model comparison between primordial black holes, making some sensible sort of assumptions of what would the mass function look like for primordial black holes versus the simplest astrophysical black hole models. And primordial black holes really were not favored. Of course, it's possible that the vast majority are astrophysical black holes. In fact, it's almost certain, but that there could be a hint for a few primordial black holes among them, for example, in the mass gaps. But that's a much more detailed argument and really not very clear. Okay, let me just say there are the optimists out there: Bernard Carr, Juan García Bellido, Sebastian Kless, etc., Florian Kernel. So if you want to see a more optimistic take on the evidence, have a look at this paper. Now, related to the LIGO mass is the QCD phase transition. So it's a smooth crossover. It's not really a phase transition, but nonetheless, when the quarks get bound into hadrons, what happens is the equation of state, which for radiation would be 1/3, drops a little bit at a given temperature around the QCD scale, which in terms of horizon mass, you can convert to being basically the solar mass. What does it mean? Well, in terms of FPVH, here the mass function rather than a single number, because we're not talking about a monochromatic mass function, it would boost the mass function by many orders of magnitude for a given amplitude of primordial fluctuations. Why? Well, basically because the mass function is exponentially sensitive to the collapse threshold. And when the radiation pressure is reduced, even by of order, say 20%, that leads to an exponential enhancement in the primordial black hole mass function. And so there's some hope to motivate that we should see, if primordial black holes exist anywhere in the relevant mass range for LIGO, Virgo, Cancri, there should be a boost to the subsolar number density. And that would be great because that's below the Chandrasekhar mass, meaning in normal astrophysics, you wouldn't expect black holes or neutron stars to form with such a small mass. So a potential smoking gun signature. But although LVK has sensitivity, it hasn't found at high significance any such events. And this also relates to the pulsar timing array. So this was very exciting, and this is only a few, well, I guess it's now 3 years ago. There was the first detection of a stochastic gravitational wave background. So different from seeing individual major events, this was seeing basically all of space rippling around us in every direction, just like the CMB is. You know, it's a uniform background coming from every direction. Where does this pulsar timing array signal come from? The astrophysical, the expected signature is supermassive black hole binary and spiral, not seeing the final merger, but seeing sort of, supermassive black holes inspiraling around each other from all over space and at a variety of redshifts. However, this is not a perfect fit, and there's been a huge flurry of papers, especially in 2023, of people looking at alternative sources. One of the most popular being so-called scalar-induced gravitational waves. What is that? Well, for those who've done just a first cosmology course, what you're probably taught, and this is not wrong, in general, is that the scalar, the vector, and the tensor fluctuations decouple. Okay, and that's true, but it's only true at first order in perturbation theory. So at first order, it's good. And yes, on the CMB scales, the perturbations are very small, so first order perturbation theory is certainly extremely accurate. But on much smaller scales, as I showed you, we only have constraints, and the constraints are rather weak, of order 10 to the minus 2. So it's possible the perturbations were much, much larger on these small scales. And then the scalar perturbations, if they're of order 0.1 or 0.01, will generate, in fact, an observable amplitude of gravitational waves, second order, so hence the scalar-induced gravitational waves. Very roughly speaking, the amplitude is proportional to the power spectrum of scalar fluctuations squared, because it's a second order effect, so you need the square of the linear fluctuation to generate anything, and then it's redshifted like the radiation. So you can, again, just as you have a single relation between scale and horizon mass, you also have a relation between, a one-to-one relation between scale and frequency. So you can ask, well, which mass or which horizon mass would correspond to the frequency which pulsar timing array is detecting gravitational waves, and by coincidence, it's again approximately solar mass. So let me now highlight this point in the plots where I've shown the pulsar timing array constraint. Again, it's a function of the assumption of the peak of the primordial power spectrum. Okay, how this relates to primordial black hole. And you can see by, again, either by coincidence or by a hint of new, exciting new physics, that the amplitudes required are almost exactly the same. Meaning if pulsar timing array is seeing the impact of scalar-induced gravitational waves rather than all the other potential reasons, we should also be seeing primordial black holes with the corresponding mass. Again, you can map from frequency to horizon mass, well, to length scale to horizon mass, of around the solar to 100 solar mass, which is exactly where LIGO, Virgo, Cancri are sensitive. This plot was made before the PTA detection, but of course people have revisited this much more carefully since then. The conclusion is, again, that the devil is in the details. It's difficult to reconcile in detail these two values. But also, I would say there are still remaining, not quite order of magnitude, well, certainly not order of magnitude, but order 1 perhaps, certainly more than 10% uncertainties in exactly how to map both scale to mass and how to map amplitude or a variance of the primordial power spectrum to the primordial black hole number density. So it's challenging, but in my view, not excluded that these two things are seeing the same physical effect. And another challenge is that the QCD transition is going on around these scales, and you have to take that into account as well. And this is all getting, to say the least, rather complicated. So exciting times. But as I said, for me, the smoking gun signature would be the detection from LIGO Virgo Kagra of a subsolar mass, a definitely subsolar mass compact object. And that hasn't been found. And the longer the searches go on and don't find anything, the more it becomes intention to explaining pulsar timing array and primordial black holes via the QCD phase transition. So it's still interesting, but it's looking more and more squeezed, is my honest verdict. But I would also say, that a really precise calculation to fully convince everyone really needs to involve numerical relativity simulations, which are extremely challenging. And in my view, the answer is not really known yet. Okay, now let me go to the very light end. And remember, the asteroid mass window on one side had microlensing constraints to the heavier side, and to the lighter side had evaporation constraints. Okay, so evaporation, well, there's the famous Hawking result from the 1970s, semi-classical result that the temperature goes like 1 over the mass of the black hole. So if you put in solar mass and set the units, and the temperature is completely negligible, even compared to the CMB temperature, so we'll never observe Hawking evaporation from any astrophysical black hole. But if we have primordial black holes again, because the early universe had arbitrarily high energy densities, the mass can be as small as you like. And hence it's possible that we have very small mass black holes with observable Hawking evaporation, or which have even fully evaporated by today. If you integrate this relation, you find that the lifetime of the black hole is proportional to the mass cubed. If you put the lifetime equal to the age of the universe today, you find that the initial mass you need is of order 10 to the 15 grams. Okay, so those mass primordial black holes, if we were so lucky that they formed, they would be exploding today. And towards the end, they get extremely hot. The evaporation becomes extremely fast, and we really should see basically a black hole exploding, which would be very exciting. And well, there was a claim that we have found that from just last year. Okay, so this was the optimistic view. There's this famous KM3 ultra-high energy neutrino was the result of an evaporating primordial black hole, the final split second of evaporation. It was optimistic, as they say. Let me try and explain why it's so optimistic. So it is true, first of all, that as the mass goes to 0, the temperature goes to infinity. So you can generate arbitrarily high energy particles. But apart from the sort of fine-tuning to have formed one with a mass such that its lifetime is exactly equal to the age of the universe, we can think intuitively. Let's say you really do form in arbitrarily high energy, then you can ask, well, when the black hole was 10 times heavier, the temperature was 10 times less. And the energy in the black hole, remembering E equals mc squared, was 10 times larger. Okay, a black hole 100 times larger would have 100 times more energy to evaporate. So for every ultra-high energy neutrino, you should expect vastly more lower energy neutrinos as well. And so the calculation done after this paper, this PRL, was asking, well, exactly that question. Okay, if we do see these exceptionally high energy events, why didn't we see many others from IceCube, for example, which sees also high energy neutrinos, but slightly lower, or from gamma rays, so from photons. And unfortunately, we didn't see any other signs of the signature of that exploding black hole. So it seems like a huge coincidence that we just see the ultra-high relativistic event, but not the slightly lower energies. Well, theorists are very creative, so they tried to resolve this problem by saying, well, you may have heard of Diwali's idea of memory burden. of black holes, saying that Hawking evaporation ends much more quickly than we expect, long before you get to the Planck mass. And then the evaporation slows down. There can be extra dimensions, etc. There could be a spin of the primordial black hole. And this does add more freedom, but to be honest, the challenges still remain quite severe. At least that's my view. So to just try and make that a bit more concrete, again, from this Eroldi et al. Paper, this is showing the flux in neutrinos, gamma rays, protons, etc., electrons, positrons, in the last day and dashed. Then when you get to the last minute, the black hole has got lighter. So the number, as I said, the number of events will go down because the amount of energy left to radiate is much less, but the energy scale has gone up because the temperature's gone up. And so hence you can reach higher energies. And the observed ultra-high energy was around 100 petra-electron volts. Remember, this is way off the scale. This is way above anything CERN LHC can reach. Basically, you have to be in the last 10 to the minus 3 seconds of evaporation. But the black hole, being at, even if it's in, in our galaxy, it still won't really have moved in the last day. So we should have seen this huge stream of particles, and we didn't. So that's a big challenge to explaining this ultra-high energy neutrino. Again, there are more freedoms, as I said. You could have extra dimensions, you can have memory burden. So a work I did recently with Itzi Tamayo, a PhD student of mine, was to see if you had extra dimensions, a Rundle-Sundrum 2 model, where you've got one where we're confined to a brain, but where small black holes would in fact fit within the warping scale of the brain and hence change their properties, change their lifetime, change their temperature, etc. It turns out that the asteroid mass window, which is shown here on this back plot, starts to get larger, and depending on the scale, the sort of relevant length scale of this extra dimension, you can make the asteroid mass window larger. Basically, you go to smaller scales. The microlensing constraints really don't change at all. We showed that. And it's possible this dashed line shows where you move from a 4-dimensional black hole to, from a standard black hole to an extra dimensional black hole. And it is possible that dark matter are extra dimensional black holes. If they are, though, whether we will ever be able to know that, I'm afraid I'm not so optimistic. In terms of the memory burden, again, a very interesting, relatively new idea. It's to do with entropy arguments. That the argument is that once you've emitted more than half the mass of the black hole, it's entropically no longer favored to evaporate quickly, and hence the memory burden basically slows down the evaporation a lot. But it's unclear if this also widens the mass window or not, because it depends on the transition from Hawking to memory burdened evaporation. And the initial idea was, well, these basically become very stable and hence they're dark matter candidates. But we have very precise constraints, not just today, but also from the CMB and from Big Bang nucleosynthesis. And that's, evading those constraints over all of those timescales becomes very difficult. Just to mention one other idea, relics. So again, worked on one of my PhD students recently, Majorana-Raychaudhuri, was looking at the idea that if evaporation does continue down to more or less the end, then we know the semi-classical Hawking result should break down by Planck scale. What happens then, nobody knows, but one possibility is that you form a Planck mass nugget or relic. And then this is basically a nightmare additional scenario, the Planck relic window, where all of dark matter are in Planck mass nuggets. Very, very hard to probe, if at all possible. And they will be neutral, electrically neutral, so basically they're very hard to see. The best hope is probably via signatures from their formation or their evaporation. But if all of that is complete before BBN, then it becomes really very challenging. Okay, I'll just very briefly, I know I'm nearly out of time, but say that there are lots and lots of dark matter candidates. Of course, primordial black holes are special. I'm not saying they're better than any other. So let me just briefly flash that if we have WIMPs, which until a few years ago were probably the most popular dark matter candidate, plus primordial black holes, then around every primordial black hole, if they are just a small fraction of the dark matter, you would expect a huge number of WIMP particles. And they will be gravitationally attracted, but very rarely actually fall into the black hole because the event horizon is so tiny. Okay, so you should expect a large number of WIMPs to be gravitationally bound around all of the primordial black holes. They would have a very large density. We did a numerical simulation of this. This is going back quite a long time. And when you've got a very large density, then you should see WIMP annihilation signatures. And so, yeah, the detection of WIMPs basically is incompatible with having primordial black holes because we should be seeing WIMP, basically a bright signature of WIMPs annihilating into standard model particles, and vice versa. If we did detect primordial black holes, then there can't be WIMPs. So even if you really detect a single primordial black hole, you've ruled out WIMPs being the rest of the dark matter. So here's my penultimate slide, just to say, although, in my view, lots of dark matter candidates, including primordial black hole relics, are probably not testable, primordial black holes, which are heavier, those not yet evaporating, should be seen indirectly at the very least, even if there's only one inside the whole observable universe, indirectly via the scalar-induced gravitational waves. Now, I am not including astrophysical foregrounds, etc., but it should be high enough here that really, if there are any primordial black holes, at least for Gaussian initial conditions, we would see the associated gravitational waves from the production time via the square kilometer array or LISA or Einstein telescope, or there are many other, future experiments coming up. So at least this is a promising future for this search. So to summarize, for now, primordial black holes are still a viable dark matter candidate. They can form with any mass, and hence you can probe the initial conditions really on any scale, because there's some mass corresponding to any initial scale. There's potential links to supermassive black holes, but the distortion constraints are very tight. The LIGO-Vega-Cagra events, pulsar timing arrays, evaporation. Arbitrarily high energies can be reached, but again, hard to explain the ultra-high energy neutrino. And in my view, within of order a decade, perhaps 20 years, we should really be able to rule out or detect primordial black holes as all the dark matter, unless they're reds. And I'll stop there.